Hello friends, welcome back in the lecture series on the reactions of the benzene. In our earlier lecture, we have finished the reactivity of benzene, aromatic electrophilic substitution reaction, and we have also seen some of the mechanism of some of the aromatic electrophilic substitution reaction like nitration, Friedel-Crafts alkylation, Friedel-Crafts acylation, and the nuclear halogenation. In continuation to these, in today's lecture, we will cover the two important reactions shown by the benzene and its derivative. One of them is side chain halogenation and second one is Birch reduction. First of all, we will try to understand what is nuclear halogenation and the side chain halogenation. So we have already studied the mechanism of nuclear halogenation in our earlier lecture, where we studied in detail the mechanism of chlorination of benzene. Today, we will try to understand what is the difference between nuclear halogenation and the side chain halogenation. So in order to understand the nuclear and side chain halogenation, you have to think of a benzene system containing one side chain. Say this CH3 is a side chain of a benzene ring. So we know that when you treat it with chlorine and a Lewis acid like FeCl3, the electrophilic chlorine will go to the benzene ring, means onto the nucleus, and you will get a mixture of ortho and para chlorotoluene as a product. So this is an example of a nuclear halogenation. On the contrary, if you do the chlorination in absence of a Lewis acid, rather you do it in presence of sunlight under refluxing condition, then what will happen? The halogen will not go on to the benzene nucleus, rather it will go to the side chain, and you will get a replacement of this H of the side chain by chlorine, resulting in the formation of benzyl chloride. Now this reaction will not stop at this benzyl chloride level, rather it will further undergo the subsequent chlorination, again the side chain chlorination, resulting in the formation of dichloromethylbenzene and then trichloromethylbenzene. So this is how this is a toluene is a very good system to understand the nuclear versus the side chain halogenation. So here you can clearly see that in presence of Lewis acid like FeCl3, nuclear halogenation takes place, but in absence of Lewis acid, rather in presence of sunlight, a free radical pathway will take place and will result in the formation of side chain chlorination. Now, what are the important points that you need to find out related to these two reactions? In the context of nuclear halogenation, the substitution takes place on the benzene nucleus, whereas in side chain it takes place on the side chain. And as I mentioned, you need to have a Lewis acid catalyst in order to do the nuclear halogenation, whereas for side chain halogenation you does not require any catalyst, rather you require sunlight or the reflux condition in order to generate the free radical. And as usual, the nuclear halogenation involves the aromatic electrophilic substitution mechanism, which involves uranium ion as an intermediate, whereas side chain halogenation involves the free radical mechanism. Now we'll try to understand the side chain halogenation in detail. Here, replacement of you know that side chain halogenation is the replacement of hydrogen of a side chain of the benzene nucleus by halogen. So toluene on treatment with chlorine at reflux temperature in presence of light gives benzyl chloride, then benzyl chloride, and subsequently benzotrichloride. So this is a representative example of the side chain halogenation. It is important to note that benzyl chloride is also known as chloromethylbenzene. Benzyl chloride is also known as dichloromethylbenzene. Benzotrichloride is also known as trichloromethylbenzene. So you can name, one way to name these compound is to name it as a methylbenzene derivative. So this toluene is also called as methylbenzene. So when you put one chlorine, it becomes chloromethylbenzene. When you put two chlorine, it becomes dichloromethylbenzene. When you put three chlorine, it becomes trichloromethylbenzene. Now, looking at the mechanism, as mentioned earlier, this is a This particular mechanism involves a free radical pathway. Now in the free radical pathway, what happens? In the free radical pathway, what happens? There occurs a 3 steps. What are those steps? The steps are initiation step, propagation step, and the termination step. You take any free radical mechanism of the organic chemistry textbook and you will find these 3 steps, which are very common. What are those? Initiation, propagation, and the termination. So what happens in the initiation step? The homolysis of Cl2 results in the formation of Cl dot. And what is where from the energy comes from? The energy comes from the sunlight and the heat. So homolysis of chlorine takes place, resulting in the formation of chlorine dot. The next step is a propagation step. This initiation step involves the formation of free radical. Propagation step involves the attack of free radical, resulting in the formation of another free radical. So looking at this propagation step, which is again consisting of substep A and substep B. In the substep A, what happens? Now you have a chlorine free radical in your flask and you are having a toluene system with you. Now what will happen? For the sake of convenience, I have written toluene like this, C6H5CH3. Now what will happen? Free radicals are better known to extract the H dot. So, there is one typos on this slide. Make sure that Cl dot, every time dot should be a superscript. Every time, like here H dot should be superscript. This one looks okay, this one looks okay, but here it doesn't look okay here. Okay, so the thing is, free radicals are known to abstract the hydrogen, and homolysis of this carbon hydrogen bond will take place. H dot will go with Cl dot to form HCl, and you will end up getting a benzyl free radical, C6H5CH2 dot. Note here that a dot is on the side chain carbon, okay, on this carbon. Thereafter what happens? Now you have a benzyl free radical and you have a chlorine, because in a reaction flask you have chlorine as well as the toluene. Now what will happen? This benzyl free radical eventually attacks on the fresh molecule of chlorine, resulting in the formation of benzyl chloride and a chlorine free radical. So why this step 2 is called propagation step? It consists of substep A and B. And why it is called propagation step? Because you start with one free radical and you end up getting another free radical. So in the first substep A, you are getting a chlorine radical is being reacting and you are getting a benzyl free radical. In the second step, your benzyl free radical is reacting and you are end up getting a chlorine free radical. So these are the two steps, substep A and B, which are repeated end over end. End over end means once the substep A is over, B will start. Once the B is over, A will start. So these two steps, substeps A and B, are repeated end over end, and this will result in the propagation of a chain. That is why this reaction is called, this step is called as propagation step. And in the next step, what happens? Now the last step is termination step. Now the above chain reaction, propagation step, is also called as chain reaction. So above chain reaction is terminated by combination of any two free radicals. So in your flask, how many free radicals you have? You have two types of free radical. One is Cl dot, other one is benzyl free radical. So by permutation combination, you can write the three different reaction: combination of two Cl dot, combination of two benzyl radical, combination of Cl dot with benzyl radical. So this is what is represented here: combination of two Cl dot, combination of two benzyl radical, combination of benzyl radical with chlorine free radical. These are the chain terminating step. So this is how you can explain the side chain halogenation, which is, this mechanism is very similar to the halogenation of methane. Only thing is, in methane you have here CH3 and H you have, instead of H you have here a phenyl ring. Otherwise the mechanism is very similar. Now moving forward, we are now heading towards one of the most interesting reaction in organic chemistry, and it is called Birch reduction. Now what is Birch reduction? You know that benzene ring can be reduced by 3 hydrogen into cyclohexane. So Birch reduction refers to a reduction wherein you are reducing the benzene ring partially by using sodium or lithium metal in ammonia. So the partial reduction of benzene ring by sodium or lithium metal in ammonia is called as Birch reduction. So benzene when reduced with sodium or lithium metal. Why sodium or lithium metal? Sodium and lithium belongs to the first group of the periodic table, and they are having very low ionization energy, and they are very eager to give away their, because their outer electronic configuration is ns1. So that electron in the outermost orbital can be easily given out and attaining the octet. So sodium or lithium metal, when dissolved in ammonia, what happens? Why you need liquid ammonia? Liquid ammonia is needed here because ammonia is a solvent which can solvate electrons. See, this is a new concept. Solvation of electron means you are getting a solution of electron in ammonia. So when you add sodium metal to liquid ammonia means ammonia gas which is liquefied under pressure. Because there is one more term which is common in chemistry, which is called liquor ammonia. Liquor ammonia, Liquor. Liquor is somewhat different than liquid. Liquid refers to the, you have done the what you can say, the condensation of the vapors of ammonia into the liquid. So that is called liquid ammonia, means ammonia in a liquid state. On the contrary, liquor ammonia refers to saturation of water with the ammonia vapor. So when you saturate water with ammonia vapor, you will get ammonium hydroxide, and that is called as liquor ammonia. Okay, so here liquor ammonia cannot be used. Here we have to use liquid ammonia. Now what happens? So benzene, when treated with sodium or lithium metal in liquid ammonia, as I mentioned, this will, when you sodium metal will give up its electron, and these electrons will be solvated by the liquid ammonia molecules, and here your solution will appear, solvated electron appears blue to the human eye. So very fantastic appearance to this. And you need some solvent which will act as a source of proton. I'll tell you why you need a source of proton. To give a non-conjugated cyclohexadiene, you get a cyclohexadiene which is non-conjugated. So here we have seen the diene, the conjugate dienes which are having separation of more than one single bond, they are referred as non-conjugated dienes or isolated diene. So here non-conjugated cyclohexadiene, and when you do the Birch reduction of the benzene ring, you will get, and note here only 2 hydrogens are added, means out of the 3 double bond only 1 will be reduced, 2 will remain intact with the concomitant rearrangement, reposition, not rearrangement. So here you can see that you get addition of 2 hydrogens, 2 double bonds are intact out of the 3, and you get a non-conjugated cyclohexadiene as a product. So this is a very interesting reaction, and this reaction proceeds via electron transfer reduction mechanism. Because reduction, as the name itself indicates, reduction can be defined in 3 ways. Number 1 is addition of hydrogen, number 2 is loss of oxygen, and number 3 is gain of electron or addition of electron. So here what is happening, you are adding an electron to the benzene ring, and when in the first step electron addition takes place, that type of reduction is referred as electron transfer reduction. Sorry. So this reaction proceeds by electron transfer reduction mechanism. A very unusual mechanism. Probably you have not studied this kind of mechanism up to your 10+2 level. So it involves electron transfer from sodium metal to benzene through a solvent which is liquid ammonia in this case. As I mentioned, so what is happening? Transfer of electron from sodium to benzene ring through liquid ammonia. So liquid ammonia is acting as a medium to solvate the electron in this particular reaction. Now we'll try to understand the mechanism. As I mentioned that Birch reduction involves the electron transfer from sodium metal to benzene via ammonia. So what will happen? In the first step, sodium will give up its electron because of its low ionization potential. Ionization energy of sodium is very low, so it will give up its electron and Na positive, which will retain the octet. This electron will be solvated by liquid ammonia. These electrons will be taken away by the benzene ring. Now the benzene ring, when takes up one electron, what will happen? Benzene ring, when takes up one electron, there are already 6 pi electron and you are adding one more electron. So you count the number of electron on either side. On this side you have 6 pi electrons and you are adding one more electron. So how many electrons are there? 7 electrons. So here what will happen? 1 pi bond, 2 pi bond, 1 negative charge. So how many electrons are there? 6 electron, and a dot means total 7 electron. So this dot, this electron will go here, and subsequently there will be a movement of an electron on the other side, resulting in the formation of the radical anion 1. And what happens in the subsequent step? Now you have a negative charge and a dot here, so it is called as radical anion. And just for the sake of simplicity, I have labeled it as 1. In the subsequent step, what happens? Now you have a radical anion with you. It will take up the proton from the solvent, which is ROH, alcohol. You can take any alcohol, ethyl alcohol, methyl alcohol, as a proton source. Now this negative charge will take up the proton from the alcohol, resulting in the formation of radical 2. So radical anion 1 is getting converted into radical 2 after protonation. Now the third step is again one more electron transfer, because you have added one hydrogen only in the step 2. One more hydrogen is to be added, and before adding one more hydrogen you need to add one more electron. So electron transfer from the sodium metal to the radical 2 to form anion 3. So this radical will take up one more electron and it will be converted into a negatively charged species, that is anion 3. And in the last step, which will be a replica of the step 2, it will take up the proton from the alcohol to form 1,4-cyclohexadiene, which is the product of this reaction. It is very easy to remember this Birch reduction mechanism. Step 1 and step 3 involves the electron transfer. Step 2 and step 4 involves the protonation. So one can develop one mnemonics. What is that mnemonics? The mnemonics is EPEP. EPEP means electron transfer from sodium to metal, sodium metal to benzene. Step P means protonation. Electron transfer, protonation, electron transfer, protonation. This is how you can keep this mechanism in mind, and this is a very important reaction in the context of organic chemistry. So I'll stop here. Thank you for your kind attention.